Welcome to our presentation on using machine learning to improve public reporting on U.S. government contracts. I'm Daniel Reich from Naval Postgraduate School, and this is joint work with my collaborators Bill Muir and Roger Westermeyer from the U.S. Air Force Installation Contracting Center. So the U.S. government purchases a wide range of goods and services, and those purchases are categorized for analysis, budgeting, forecasting, other purposes. And the way that they're categorized is they're classified using product service codes into a hierarchical taxonomy. So for example, if you're going to purchase vaccines, that might fall under the category medical. There are 2,915 classification codes in the US government's taxonomy, and those are grouped under 19 parent categories. So if you are the contracting specialist that's trying to put together a contract for a purchase, how do you find the right code for that purchase with so many options available? The U.S. General Services Administration, or GSA, publishes a manual called the Product and Service Codes Manual, and it's 320 pages long. And if you search for vaccine, what you'll find is there's no results. That word is not even in this manual. So if you are, again, trying to figure out the code that you need having to do with vaccines, trying to search the manual for vaccines is not going to give you any information. So you might think, okay, well, vaccines have to do with medical. Why don't I search medical? And if you search medical, what you're going to find is medical appears on 42 pages in this manual. And in fact, it appears 302 times. That's also not very helpful because to review every part of this manual where medical is mentioned, trying to find which one might be for vaccines, it's going to be a time-consuming task. So what we did to help solve this problem is develop a prediction engine using machine learning for product service codes. So if we enter the term vaccine in our search engine, in 78 milliseconds, our classifier has searched for vaccine and identified 8 potential product and service codes that might match. The top result is drugs and biologicals. And all the information that you see here is associated from that GSA manual. And so if I'm the contracting specialist, I go into the system, I found this, and I say, yeah, this is actually the code I need. I can select the code, and the system captures that information. So this is a very quick process. I could also search coronavirus. And similarly, I'd get different results. The first one this time is medical and surgical instruments, hospital furniture, equipment, utensils, and supplies. You can see these are terms that may be relevant. So how can we be confident, though, that the results returned are the right results? Well, one, domain experts have validated some of the commodity groups. Through our machine learning modeling, we validate the model on about 600,000 historical records during training, and then we test the model on an additional 600,000 holdout records after training is complete. So those both give us confidence that the model is effective in identifying relevant codes. The other way that we collect information on this is, as you saw, users can validate search results within the web application, so we can get feedback. Here's a process flow diagram that at a high level shows the contracting process with and without our application. So you have some sort of goods or services that you need, and the example we've been going with, that's vaccines. You have a contracting office that's going to receive a request. We need a contract to get this. An officer is assigned to prepare the contract. They have to gather info. And this is where they try to select the most relevant code. So with our app, that person will review the request, the description details. They can search in the application. If they don't get the right code, they can try again with another code, search again, repeat, just like you do, if you don't get the right set of results when you search on Google. If the application is not giving you what you need, you always have this backup option of returning to that PDF manual that we looked at. Compared with without our model, all you have at your disposal is a manual to try to search through to find that relevant code. So our application is making this process of identifying the right code much easier and much quicker. Ultimately, the officer that's assigned to prepare the contract is responsible for ensuring that the code entered in the contract is the correct one. Part of the reason that the impact of our application is so significant is due to the scale. The U.S. government executes hundreds of thousands of contracts annually, and in fact has averaged 860,000 contracts or so over the past 5 years. What you see in this figure is the relationship between how much time on average is saved per contract by using our application, and the savings that results from that measured in full-time equivalents of personnel saved. So we have had one group estimate that they save about 30 minutes per contract on average. That estimate would translate for 110,000 contracts into 26 full-time equivalents. We have plotted a range of this, of course, because it's hard to obtain an exact estimate on the time saved, given how widely spread the use of our application is. But clearly, with this volume, that savings is quite substantial. So now let's talk about some of the descriptive analytics. To approach this problem of classifying contracts analytically, you need data. And we relied on the Federal Procurement Data System, which contains transactional metadata on U.S. government purchases, and reporting for these purchases is required by law of federal agencies, except in cases where maybe the purchases are classified, so that's a small percentage. But generally speaking, purchases are all recorded in the system. We were able to obtain 6 years of recent archival data from 2014 to 2020. That data required a lot of preparation. The formatting wasn't necessarily consistent from year to year. And we were left, after we dealt with all that, with 4 million records. And 2 of those fields in particular are useful for classification. One is the product service code itself, and the other is a free text description. Those text descriptions are where we're getting our information from. And there is terse tweets. Less than 8% have greater length than 120 characters. The current max character length is 250 characters. That's since June 2019. Before that, it was 4,000. So you can see when people write out these contract descriptions, they're not taking a lot of time to do so. They're just putting in a little bit of information. But even so, we're able to really leverage that given the volume of data that we have. The descriptions, on top of being short, have acronyms, abbreviations, misspellings. So you see things like hydraulic here is not spelled correctly. Pressure is abbreviated into press. There's all sorts of codes flying around this data. So this is challenging data to work with. On the descriptive analytics front, we already reviewed there's a PDF manual published by the General Services Administration. That's the official manual. That manual is compiled by hand and it's updated by people. What we've done is auto-generated a version of that manual with NLP, pulling information from the manual itself and complementing that information with terms that we can extract from the historical data. So the way that we auto-generate this PDF manual is we use natural language processing on those 4 million historical records. And so if you imagine starting with, take just one document, the raw document is going to have an ID associated with it. It's going to have the ID of the code that's associated with it. So that's the class ID. It may have some embedded tags that are not of interest and we want to process those out. And then it's going to have a description. So in this case, imagine cleaning services for hospitals as a description. So you trim those tags, you put the whole thing in lowercase, we tokenize it, so that splits up the words. We stem those words, so for example, cleaning becomes clean. We remove words that are called stop words that aren't overly important, things like for or the or in. And then you have a process document. You combine those process documents together into a term presence matrix, where that tells you for each document, does any given term appear or does it not appear? So it's ones and zeros. And then you can roll up that matrix into a class matrix, which has frequencies. So if term 1 appeared in 2 documents that both were class 1 documents, you'll have a 2. And then you can normalize by row. When we have this normalized matrix of information, that's basically our codes against terms that may be associated, we're able to define weight cutoffs to select those terms, and in so doing, are able to construct a manual with a lot of additional information that may be searchable and quite useful for people that are referring back to it. Now Bill's going to talk about the predictive analytics.
Hi, I'm Bill, and I'm going to speak with you today about the predictive analytics component of our application. This predictive component uses machine learning models, and what we're attempting to do is take a textual description of a contract requirement. So someone has described a requirement, and then given that description, we want to predict what is the correct code out of this taxonomy 2,915 potential codes. This taxonomy describes nearly every product and service that the government purchased, which is a very wide range. So it's a challenging problem given the amount of text and the number of potential codes. What the model does at inference time is that given text, it assigns a probability to every single code. And what we present to the user in the application is only codes that have at least a 1% probability determined by the model of being correct. This typically shakes out on average to maybe about 10 or 12 codes that are being presented to the user out of 2,915 possible codes. Daniel mentioned earlier that the data we're using for this application comes from the Federal Procurement Data System. We use several years of historical data, accounting for several million records, each from a contract. And then we split this data, as is commonly done, between one set for training, one set for cross-validation at training time, and a third holdout data set for testing. We really wanted to start off with a nice baseline of what we should expect model performance to do. This, we relied on the tried and true naive Bayes multinomial classifiers. We fit three separate model types. The first model type is a word level model with a little bit over a 4,000 word vocabulary, which is what was derived from the descriptive analytics. The second is a word level model with a much larger vocabulary, to the 18, which is a little over 250,000. And the third is a character level model. The difference here is that for the word level models, we're taking a string of text and we're breaking that string apart on the word boundaries. For a character level model, we're taking a string of text and we're breaking that string of text apart at each character. We reach the highest level of accuracy with the word level model with to the 18th size vocabulary. The character level model performs noticeably poorer. One item of interest here, though, is that when we're talking about performance, we're talking about accuracy. This truly is selecting the top code, correct code, out of the 2,915 possible codes. So you can think of this if we had a 2,915 sided die. Assuming uniform distribution, then the probability of randomly selecting the correct code would be quite low, far less than 1%. So an accuracy that approaches 0.46 is a substantial improvement over that random case. Our next step was to fit character level convolutional neural networks. One of the advantages that we see, and what the literature tells us about character level modeling, is that when there's a lot of misspellings or abbreviations or acronyms or issues in word morphologies and so forth, then the character level models may actually perform better than a word level model. This is important because as we've looked at the text, the data that we've seen, as we understand the data that's input into the application, users often describe their requirements and they search with typos, they use joined words, they use abbreviations, they use acronyms, and things that are likely to be either out of vocabulary or just simply not show up in the vocabulary at all. We want to be able to handle those gracefully. Here, we are also using convolutional neural networks. These are inspired by biological neural network, which has been shown to outperform more traditional statistical learning approaches, such as we use for our baseline Bayesian modeling. This graphic depicts the architecture for our convolutional neural network from Zhang et al. 2015. You can think of the text kind of flowing through this network, and it begins with an embedding layer and then passes through, after embedding, a series of convolutional layers with some pooling, and ends out into dense layers, or what's termed fully connected layers. And that last layer, the purple layer on the right, is a softmax layer where the probability is computed for each class. The inputs that are going into that embedding layer on the far left are sequences of encoded characters. Again, recall that we are splitting the text on character boundaries. Those characters are then encoded as integers before they are input into the model. You can see here on this chart the characters that we elect to use. There are, of course, other characters or runes that could be used, but these are the most common characters. One of the more interesting components of the problem that we're working on here is that the taxonomy itself is hierarchical, and this is actually quite common. The clusters themselves contain information and can be used to improve prediction. There's a series of different approaches that have been taken. One is what's termed a bottom-up approach. In this case, we're essentially only predicting at the leaf node level, the nodes at the very bottom. So PSCA, PSCB, PSCC in both the left and the right figures. We are, in this sense, flattening the taxonomy. A second approach then accounts for the hierarchical nature and the clustering within the taxonomy is to take a top-down approach. So we can classify first the level below the root node, and then from there classify at the leaf level, and then use both the predictions at the category level and at the leaf level in concert to make what we believe to be better predictions. The figure on the left shows the product service codes in a hierarchy with parent categories. The figure on the right, it's a related but separate problem where we have all the product service codes in those leaf nodes, but each can only be assigned to a parent category binary problem of it either being a product or a service. So in this chart, you'll see the results of classifier performance. What we've done is we fit models to three different problems. problems. And we've addressed the hierarchy for each one of those problems in two different ways. These two different ways are either a top-down classification approach or a bottom-up classification approach. The three different problems are binary problem. Is it a product or is it a service? What is the correct category? Recall that there are 19 parent categories. And then the third problem, which is a problem that's most germane to our users and what they care about the most, is can we select the correct product service code out of the 2,915 product service codes? In each of these instances, we're comparing the performance between the word level naive Bayes baseline, the character level naive Bayes, and our character level convolutional neural network. Character level CNN outperforms these other models in every instance, as does the top-down classification approach that accounts for the nature of the hierarchy and the clustering. Our application takes this convolutional neural network that we've just shown to perform well, and we deploy it on a public-facing website that's available to contracting officers and contract specialists. It's also available to our industry partners to help them to identify requests for proposal. The model has been used more than 100,000 times, and usage continues to grow. The model is also accessible via an API, which can be integrated with other applications, such as the contract writing system. The classification of government spend truly is an important problem. And it's not a problem that's specific to the U.S. government. It's a problem that exists for governments across the world at federal, state, and local levels. It's a matter of transparency for the taxpayers to understand how taxpayer funds are being spent. These codes are a primary driver for how the federal government manages its more than $500 billion per year on contract spend for products and services. We were able to address what has been historically a very time-intensive and manual process and apply analytics to reduce the amount of time that's spent. We've been able to tap into a rich archival data set that's been published by the government that historically has not been used for analytics for this type of application. And one of the things we hope to achieve from this is to inspire others to work in the government and public sector space.
Hi, my name is Captain Anita Naylor, and I'm a contracting specialist in the United States Air Force. I'm here as a customer testimonial to just how awesome this tool has been for me. So when I have to look up a PSC, I go to the guidebook, I do Control F for the term that I think is most relevant. If I don't find it the first time, I use a synonym or maybe a sort of related term until I get a PSC code that I'm somewhat confident with. This takes a lot of time, and this makes me really nervous when I have to present that code to my contracting officer, and I'm not as confident saying, yep, this is definitely the code we should use. Just because I choose to put a certain code for the contract doesn't mean that someone else would make that same decision. The data is not consistent. That can lead to bad decisions based off that data. So this tool solves both those problems. It gives examples, and I know it's based on data, but also it speeds that up very quickly. It's going to pop out a potential code that I could use and other suggestions as well, versus me saying, I don't know if this is the right one, and keep flipping through the guidebook. No longer do I have to spend hours going through and looking through the guidebook, helping me save time, but also giving me a lot more confidence. Okay, this is what other people have used, and I think that this does fit what I'm going to be purchasing with this contract. Before we ever put anything on contract, we get a package from the requirement owner. So that could be a pilot, that could be a civil engineer, that could be anyone on base who needs us to buy something for them. And they have to develop a package. And part of that package is suggesting the PSC and the NAICS code. Now, if I know that they're pulling this PSC and the NAICS code from this tool, as a contracting specialist, as a contracting officer, we're going to feel a lot more comfortable with those suggestions. The US government are really trying to move to this data-driven process and decision-making. This tool achieves those goals for us. So I'm just really excited for this tool. This is what the future of contracting looks like, using modern technology to provide good data to contracting officers and specialists so that they can perform the high value work and they can not spend so much time. So as one very satisfied customer, I'm super thankful that this tool exists.